Welcome to this lecture series in group theory. In this lecture, we'll be proving Gauss's theorem, which says that the group Z mod p to the n z star is cyclic if p is an odd prime. All right, so let us recall some facts that we will need. So recall that we proved that if G is a finite abelian group, I forgot to write finite here. So suppose G is a finite abelian group and p is a prime, then G has a unique silo p subgroup. The reason for this was that any two silo p subgroups in any finite group are conjugate. Couple that with abelianness, you will see that there is only one silo p subgroup. Okay. We also showed that any finite abelian group is isomorphic to the direct product of all the silo subgroups. Okay, and long ago we showed that if we have a finite abelian group G, which has elements of order m and n for some positive integers m and n, then G also has an element of order the LCM of m and n. Okay. In the previous lecture, we showed that if p is an odd prime, then this group has an element of order p to the n minus 1. Right, and that particular element that we showed has order p to the n minus 1 was this, but that is probably not going to be important. What is important is that there is an element of order p to the n minus 1 in this group. Okay, and lastly, long ago we showed that Z mod p z star is a cyclic group whenever p is a prime. Here is a problem that again I'm going to use. That's why this is marked as star, not because this is hard. It just says that if G is a finite abelian group and G1 up to Gk are all the distinct silo subgroups of G, then the quotient group G mod Gj, which is a legitimate group because G is abelian, so you can quotient out by any subgroup you want. So the quotient group is isomorphic to the product of the remaining ones. And this is one way to prove it. But you could prove it in other ways. All right, so now let's get started. So we need to collect one more fact. So suppose we have a finite abelian group, then we want to show that if every silo subgroup of G is cyclic, then G is cyclic. All right, so it's actually very simple. So let P1 up to Pk be all the distinct primes dividing the cardinality of G. Let Gj be the silo Pj subgroup of G. Okay, and we know G is isomorphic to this product, and let's say the size of G1 is, so let me write that. So size of G1 is, let's say, P1 to the power A1 dot dot dot. Size of Gk is Pk to the power Ak. All right, so now the point is, by hypothesis, that every silo subgroup of G is cyclic. We know that G1 is cyclic, dot dot dot, Gk is cyclic. So since G1 is cyclic, G1 has an element of this order P1 to the power A1, and dot dot dot, Gk has an element of order Pk to the power Ak. And since G1 has an element of order this much, so does G, because G is after all isomorphic to the direct product of these guys. So what we see, what we deduce, that G has elements of order mod G1 up to mod Gk, right? And since these are pairwise relatively prime, mod G1 up to mod Gk, these are pairwise relatively prime because they are exponents of distinct primes. This implies that G has an element of order the LCM of mod Gi's, which is nothing but the product of the mod Gi's, because mod Gi's are pairwise relatively prime, which is nothing but the cardinality of the product, which is nothing but cardinality of G, because G is isomorphic to the product. So ultimately we see that G has an element of the order of G. G has an element of the size of G, and hence G is cyclic. So thus G is cyclic. So that proves it. If every Sylow subgroup is cyclic, then G is cyclic. The converse is trivially true, because if G is cyclic, then every subgroup of G is cyclic, and hence in particular every Sylow subgroup is cyclic. So this direction was the only interesting direction. All right. So now there's a certain group homomorphism that we haven't discussed yet in this course that we will now discuss. So suppose we have two positive integers such that m divides n. So then there's a natural map. Then we have the map Z going to this quotient group. So this is your natural map, which takes 1 to the equivalence class of 1, which is nothing but 1 plus mz. Okay. So that is a group homomorphism, but since m divides n, we see that nz is in the kernel of this map, and hence this induces a group homomorphism from this to that. It's just the first isomorphism theorem. nz is contained in the kernel of this map, and hence we have this factoring. And now here is the point. Here is what I want to emphasize. So now if suppose you have some integer which is relatively prime to m. So if a is relatively prime to m, then a is also relatively prime with n. That's trivial because m divides n. Sorry, I said something in the reverse order. If something is relatively prime to n, then it is relatively prime to m. And that's simply because of this. So therefore, if I have some member of, suppose I have some member of z mod nz star. So if a plus nz is an element of this group for some integer a, then a plus mz is in this group. Right? Saying a plus nz is in z mod nz star is exactly the same as saying that a is relatively prime to n. And by the previous line, this implies that. So thus we have a map which I will denote by phi star from z mod nz star to z mod mz star. Right, so we have a map, but it is better than just a map. It is a group homomorphism. Further, it is surjective. So this map that we get is a group homomorphism, and it is surjective. So here is something interesting happening. This map phi. Sorry, I did not write. Yeah. So this I meant to denote by phi, and this is phi star. So phi was a group homomorphism where the group structure here was coming from an addition operation, right? We know how operation here behaves, but here the operation is multiplication, so to say. So it is kind of interesting that a map which is defined by addition induces a map by multiplication, and that also is a well-behaved map. A general phenomena here, what is going on is that this is actually a ring homomorphism, but we haven't discussed rings, so we can't talk about that. So there is something more general happening here, but for now we have to make do with this. So the point is that this is a group homomorphism, and it is surjective. The fact that this is a group homomorphism is actually trivial, so this part is left as an exercise. So check that phi star is a group homomorphism. What we will do is show that it is surjective. We don't really need it for this lecture, but it is interesting enough for me to spend time on it. And it is also sufficiently non-trivial. I was a bit surprised to discover that it is not exactly easy to or straightforward to show that it is surjective. So let me show that phi is surjective. All right. So to do that for surjectivity, let u plus mz be chosen in the target group, arbitrary, where of course u is some integer which has to be relatively prime to relatively prime to m. Okay, so just pick, basically what I'm saying is pick some integer relatively prime to m and consider this element in z mod mz star. We want to say that there is something here which maps to that, and we will kind of just manufacture it. So if you, I encourage you to pause the video and try to manufacture such a thing by yourself. It is a fairly interesting, the way I know how to do it is fairly interesting. There must be some simpler way. So define x as the product of all primes, p such that p is prime, p divides n, and p does not divide u. So consider all the prime numbers which divide n and which do not divide u, and product all of them. So this is the product of all of those. That is an integer, and that is what we are calling x. So ultimately we will show that so let me write a claim, and then you'll see where this is going. So the claim is that u plus mx, or maybe I should say GCD u plus mx with n is 1. So this is an element which is relatively prime with n, and the image of this under phi star is of course this thing. So once we show that this guy is indeed relatively prime with n, we are actually done, because then this plus nz is a legitimate member of the left hand side, and hence we are done. So this is the main thing, and yeah, so maybe let me emphasize what is phi star. I'm sure that should have been clear anyway, but phi star of a plus nz is nothing but a plus mz for all a in z, which are relatively prime with GCD a comma n equals 1. So that's what the map phi star is. I hope that was clear by this line. Okay. Phi star of anything is just phi of that thing. There is no difference between phi star and phi. It's just that phi star is a restriction of phi to this thing. Okay. So yeah, so we want to show that the GCD of u plus mx with n is 1, and that's a simple exercise. So suppose q is a prime dividing both n and u plus mx, right? We want to produce a contradiction. So if q divides u, then q divides, so first of all, if q divides u, then q does not divide m, and q divides q divides mx. So let me explain. If q divides u, then since u is relatively prime with m, q cannot divide m. So that conclusion holds immediately because u is relatively prime to m. And now why does q have to divide mx? That's because q divides this. So since q divides this, and if it also divides that, then it has to divide that. So we would have that. But now since q is a prime, it does not divide m and it divides mx, it implies q divides x. Right? So q is a prime which divides u, which divides n, and it also divides x. And that is a contradiction. This is a contradiction. Why is it a contradiction? So if something divides x, then if some prime divides x, then that prime has to be a prime of the form which divides n but does not divide u. But here what we have a prime that divides u, which also divides x, and it also divides n. So I hope you see the contradiction, right? So yeah, I mean, as soon as you say that q divides x, meaning a prime divides x, it already follows that the prime does not divide u. All right, so that would be a contradiction. So therefore q cannot divide u. Thus q does not divide u. Okay, and since q divides n and does not divide u, so q already divided n, and if it does not divide u, then q divides x. That's the definition of x. But if it divides x and it already divides u plus mx, it divides u, right? Q divides x and q dividing this implies that q divides u. But that's a contradiction, because if q divides u, then q is not a prime dividing x, again by definition of x. Any prime that divides u cannot feature in this list of primes that you see here, and therefore we again have a contradiction, so I'm not writing that. So the point is that this GCD is indeed 1, and therefore the image of the remainder class of this modulo nz or modulo n under phi star is this element, which we had picked arbitrarily from the codomain of phi star, and hence phi star is surjective. All right, so now we are finally in the position to prove Gauss's theorem. Okay, so proof of Gauss's theorem, P is an odd prime again, so let P be an odd prime. And G be this group. And we want to show that G is cyclic. What we will do is that all silo subgroups of G are cyclic. So this is what we will show, and by a lemma that we proved earlier in this lecture, this will show that G is cyclic. G is after all an abelian group. If we show that all of its subgroups are all of its silo subgroups are cyclic, that will show that G is cyclic. Okay, so first we note that what is cardinality of G? Cardinality of G is p to the n minus 1 times p minus 1. That's the cardinality of G. So there is a silo p subgroup of this size, and then there are some other primes, which are all of them are smaller than 1, and you have silo subgroups corresponding to those primes. Okay, so first of all, yeah, so let P be the silo P subgroup right? The silo subgroup corresponding to the prime P. So first claim is that this is cyclic. We'll show that this is a cyclic group, but this is clear because we know that the order of this element in the group G is this, and thus I mean that's it. That's the proof. So whatever is the subgroup generated by this group, that is a subgroup of this size, and hence it has to be P, because there is a unique silo P subgroup. Right? Any subgroup of this size in G is a silo P subgroup, but since there is only one silo P subgroup, the subgroup generated by this element is capital P, and hence capital P is cyclic because it has a generator. So that is fine. And here is the interesting part. All silo subgroups of G are cyclic. So this has an interesting proof, and here is how it goes. So consider the map phi, which is the natural projection map. So this is a group homomorphism. This induces. So let me not call this phi. This is just some, I don't know. Let me call this maybe theta. This induces the map phi, which is from this group to that. So we are just using the previous, what we discussed in the previous, I think it was the previous, yeah, in the previous page. So this number is divisible by that number, and hence we have such a thing. This further induces the map phi star and we already discussed that this map is surjective and it is a group homomorphism, right? We discussed this in the previous page, so we have that. And yeah, so since this is surjective and a group homomorphism, what is the kernel of phi star? What's the size of the kernel? It is nothing but the size of the domain. Oops. The size of the domain divided by size of the image, which is what? So I'm just using the first isomorphism theorem here to make that claim. And this is what? This is p to the n minus 1 times p minus 1 divided by p minus 1, right? Which is equal to p to the n minus 1. So kernel of phi star is a subgroup of size p to the n minus 1, and hence it has to be equal to p, because any subgroup of size p to the n minus 1 is the silo p subgroup of G, and then this is equal to capital P. Maybe I shouldn't have chosen the notation capital P because one can confuse it with small p. So this is equal to the subgroup P, and hence this is a cyclic group. Yeah, so I mean we already know that this is a cyclic group. So therefore G mod kernel phi star is isomorphic to Z mod P Z star. That's again the first isomorphism theorem. Phi star is a surjective group homomorphism. So this is G. So G mod kernel phi star is isomorphic to that. And kernel phi star is P, as we just showed. So G mod P is isomorphic to that thing. But by the star mark problem, what is G mod P? G mod P is isomorphic to product of all the silo subgroups of G which are different from capital P. So it's the product of all silo subgroups of G different from capital P. That's what it is. And hence this product of all the silo subgroups of G different from P is a cyclic group, because this is a cyclic group. And hence every silo subgroup which is different from P is cyclic. And we had already shown that P is cyclic. So all subgroups different from P are cyclic and P is cyclic, and therefore all subgroups of G are cyclic, and that's it. So that proves that this is a cyclic group, and that's a beautiful, beautiful proof of a fairly difficult, I would say very difficult theorem. Okay. So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.